and it's a great pleasure to be here. And my talk is about frustrated superconducting quantum networks. And main idea of the talk to give introduction in very excited topic, frustrated solid-state systems, and how superconducting quantum network, qubit networks, can bring a new attention to frustrated solid-state systems. And work has been done at Ruhr-Universität Bochum, Germany, and just a minute. And outline of my talk composes of 3 parts. First, motivation for study, superconducting quantum networks, frustrated quantum networks. And second part, what is frustrated superconducting quantum networks, and especially what kind of interaction between basic elements we can introduce in superconducting quantum networks. And first for electromagnetic interaction, and second, interesting story which appears for some particular network lattices, for example, Kagome lattices, and it's called topological constraints, which provide some non-trivial interaction between different elements, different qubits. And finally, results, what kind of novel quantum phases, macroscopic quantum phases, and quantum phase transitions we can establish in frustrated superconducting quantum networks. Okay, first, as we hear today from nice talk of Professor Bazovich, we know about many systems we can call strongly correlated frustrated systems. And solid-state systems which provide, for example, transport properties which is not described standard textbook with a free fermions, free electrons. And idea is we have to include into account interaction between electrons. This term, for example, very famous Hubbard model. But then idea is to trace out fermions here and establish some Hamiltonian which works as a interacting spins on some non-trivial lattices. And moreover, these coefficients, exchange integrals, can be different signs and provide very interesting specific properties. And for example, 2 systems, one organic metallic material and another is novel superconducting systems which provide some Kagome lattice here and also some non-trivial exchange integrals here. Okay. Then another interesting system, magnetic macromolecules, which can be a linear system or circular system. And again, the same story. We have for one bonds, we have exchange integral is positive and another is negative. But in any way, this is just some Hamiltonian, spin Hamiltonian with different parameters which can be different signs. Okay, and then result for this so-called frustrated, natural frustrated systems, non-trivial ground state. For example, if we have all parameters the same, we have ferromagnet interaction or anti-ferromagnet interaction and all spins in the same direction. But if we have different signs of this interaction, we produce some non-trivial ground state. Okay. And then we turn to superconducting arrays of Josephson junctions. Long time ago, people tried to see what happens in diamond chain of Josephson junctions. And if you have no external magnetic field, in this case, all faces of these islands or Josephson junctions is 0. But in the presence of single flux quantum, we have two different states in a single plaquette, anti-clockwise and clockwise. And then question is, what happens in system if basic element can provide two states, and then we have interaction between basic elements. Okay, and mostly this is Hamiltonian, and long time ago people realized there is very interesting phase for some range of parameters where we have single plaquette composed two states plus interaction, and we have so-called nematic Latterjan liquid state. And then question about how it's possible to obtain this or some properties what we need for this system to observe this. Okay, and then for modern superconducting quantum networks, different types of Josephson junction interacting Josephson junction systems. For example, 3 Josephson junction in basic elements, and then we have more complicated 5 Josephson junction in basic elements. And then question is how to provide interaction between these basic elements of superconducting quantum networks. One idea was, we can see from previous talk of Professor Ustinov, and for example, we have some resonator or transmission line, which due to excitation and absorption of photons provides long-range interaction between different elements of this superconducting network. Or it's possible, for example, to make many different networks composed of many Josephson junctions, and to see very famous Ising model in transverse field, and to see what is the ground state if we produce parameters of different signs here. Okay. And finally, for this motivation, and question is observation of non-trivial quantum phases called spin liquids. And for example, we see for Kagome lattice, for some range of parameters, we have, for example, this one state and another state in different direction, clockwise, anti-clockwise, and what is the combination of this in large system. And similar story for set of Josephson junctions here. If we have, for example, one bond has a negative sign, positive sign, and then we have very non-trivial distribution of spins here. And another story is due to Phil Anderson many years ago. If we have, for example, triangle, we can produce quantum state, entangled quantum states of 2 spins for one bond and no in other bonds we have just product of states. And then we have spin liquid of these strongly entangled elements. Okay, and how we can make, for example, in superconducting network, for example, this is a dynamic system. We have a set of qubits and apply some pulses and interacting qubits, and we see, for example, this area we have for some particular time to provide strongly entangled states between, this is for 3 qubits, and in this area we can provide strong entangled of 3 qubits. Okay, with this motivation then I put 2 exemplars of Josephson arrays, Josephson network with pi junctions. Why pi junction? Because pi junction provides negative interaction in some bond. And then I consider sawtooth chain. With a model, we have Josephson junction, 0 type of Josephson junction. It means critical current is a positive here. And on these bonds, we have Josephson energy alpha Ej, and alpha can be negative. Alpha changes between -1 and 1. Then we can introduce frustration parameter, which is 1 minus alpha divided by 2. Okay, and then consider quantum dynamics of this system. We have potential energy for this network and kinetic energy. And then question is, what is the macroscopic quantum phases we can obtain here? First of all, we consider classical regime, when kinetic energy plays no role. We have potential energy, and then we see what happens. If frustration is less than this critical value, we have ordered ferromagnetic state. All phases on islands and also Josephson phases are 0 in ground state, and shows here. But if we go in this region, we have disordered state. It means single basic element can be with some vortex inside, which can be clockwise or anti-clockwise. Okay, and moreover, phases on islands has some particular value which depends on frustration. Then, for classical case, we have just some combination of different vorticity in basic elements. For example, anti-clockwise, anti-clockwise, clockwise, and so on. Okay, and then question is, what happens if we include quantum fluctuations? Quantum fluctuations. In this case, we have to provide a phase diagram for quantum case. And one parameter is just ratio of capacitance energy and Josephson energy. And here frustration. First of all, non-frustration regime, where we have just ground state ferromagnet ground state, and we have standard Berezinski-Kosterlitz-Staulis quantum transition in this case. But important is we have include in kinetic energy only energy of Josephson junctions, not capacitance to the ground. Okay, and what happens in frustration regime? Each triangle has 2 states. We have double well potential, and we have just a tunneling, amplitude of tunneling between two states in each basic element. But without capacitance to the ground, we have no interaction. It means we still have all basic elements is just independent of each other, and we have product of states, which is for basic element we have superposition of two states, and for global system we have product of these states. Something exciting. But then we have to include into account, to provide interaction, capacitance to the ground. Capacitance to the ground. In a non-frustration regime, we have still ferromagnet state and just different boundary, but also nothing spectacular. We have Berezinski-Kosterlitz-Staulis quantum transition here, and that's all. But what happens in frustration regime? This is completely different story because we have interaction. And due to this interaction, moreover, this is long-range interaction due to capacitance to the ground. And this is change sign if we go to two-dimension case. One is a coordinate and another is imaginary time. In this case, we obtain new phase, novel quantum phase, and we see what happens. In this regime, we have just a random number of vortices in one case, in one basic element or another element. And this is just so-called disordered state, and in fact, it's the product of superposition of states as before. But for small parameter g, we have interesting story. We have in coordinate, we have ferromagnet interaction, and we have ordered in one direction. But in time, imaginary time, we have anti-ferromagnet case. It's called stripes quantum phase, and this is some special entangled state. And also we have close to this part, we can find some defects in this state. Okay, and then another example, we go to frustrated 2D Kagome structure. Again, idea is to introduce in some lines, we have pi junctions, and to see what happens. Again, in the classical case, we have just potential energy, and basic element, single triangle, provides two states in frustrated regimes. Again, clockwise and anti-clockwise. Okay, but even here, without quantum fluctuations, situation like this, if each triangle can be clockwise or anti-clockwise vortex inside, we have 2 power n states. But we have this, when we go around this plaquette, we have especially constraint. The total phase here can be 0. Immediately, instead of 2 power n states, we have 2 power square root of n states. For single plaquette, instead of 64 states, we have just 14 states. 14 possible states. And also we have interesting in classical regime, interesting results. In some direction, in x direction, we have a strongly correlated system. In y direction, we have strongly correlated pattern. In x direction, we have no correlation. Okay, then we have to include into account quantum fluctuations, taking into account this strange interaction due to topological constraint, total phase equal 0. And we see what happens. We have 14 states, low-lying 14 states. If, for example, amplitude of tunneling between red and green vortex is 0, it's exactly here, we have 14 degenerated states. And then we include tunneling between red and green vortexes in this plaquette, and we see some lifting degeneration. And to see what happens if, for example, we have 3 states which is very close energy, then another states with a larger energy, and so on. This is influence of quantum fluctuations and influence of these topological constraints. We have no another type of interaction except topological constraints. Okay, in summary of my talk, and we can introduce some frustrated Josephson junction arrays, network of Josephson junctions, quantum Josephson junctions, and frustration is introduced, first of all, with a combination of 0 and pi interacting Josephson junctions, and different system can provide long-range interactions. For example, capacitance to the ground, coupling to a low dissipative resonator or transmission line. And second part is a 2D coherent frustrated superconducting quantum networks, Kagome lattice of small junctions, and long-range interactions due to topological constraints. Some phases must be, total phases must be 0 if you go around some loop. And for large system, we have many constraints. For single plaquette, we have one constraint, and for large system, many topological constraints which have to be included into account. Okay, and goal is the following: to see different quantum phases and quantum phase transitions which can appear in this superconducting quantum networks, and then try to establish specific Hamiltonian and to see very interesting quantum phases, for example, spin liquid and quantum spin liquid also. Thank you for attention.
Thank you, Misha, for your talk and also for leaving a few minutes for questions. Please, Sergey.
Does it mean that you found analytic solution for the frustrated spin liquid?
Okay. I can say for this system which we consider, obviously we can heavily based on some numerical analysis or some approximation like mean field theory. For example, for quasi-1D system, because it's long-range interaction. Moreover, this is with different sign. You can just to use mean field approximation for this. And this is first part. Second part, connected with 2D Kagome lattice, you have to include, due to very small number, total number of states, not 2 power n, 2 power square root of n, you can go to, again, for numerical analysis for larger system, much larger systems than standard case.
Okay, thank you.
More questions? I'm wondering for this dynamical coupling in the first case. So you have this capacitance to ground, which is needed for coupling. Is capacitance of the order of the junction capacitance?
No. This is, we can see the case when this is C0 much smaller than standard case, much smaller than capacitance of the junction.
Okay, so this
It's not necessary to be just that.
it has to do with the
It's a standard.
with the split level separation and not with the net energy of the junction.
No.
Understand?
No.
Okay. And
This
then
is just provide some small interaction, but important is this is not nearest neighbors interaction. It's long range like you have photon in resonator. But just one important point. This is power dependence, not just the same interaction between for large system. This is decay, but some power decay is 1 divided by r squared.
But pi junctions you don't necessarily need. You just consider a general case of alpha varying from negative to positive. So if one does this experiment simply with conventional junctions, would one see these phase transitions as well? I think so.
Okay, point is, and you have to create in single element double well potential. There is a mapping if you just work with magnetic field for flux quantum, and all junction are positive, standard flux qubit. The same story.
But then you have coupling between flux qubits, right?
Yes, but then we have a coupling between flux qubit. But point is, in this model, you have just one point in magnetic field. You have in magnetic field, if you change magnetic field from this point, immediately you have double well potential, not the same amplitude.
Okay, you need to have the resonance frequency of the. The double
for this
potential
model is very important. For this model, be the same type of potential. So double well potential without splitting between potential wells. Minimum of potential wells.
You mean it should be symmetric double well potential?
Yes.
Okay, but then you have some split levels.
Yes.
And then you want to adjust the frequency of the split levels to another frequency which is dictated by capacitance. What is this frequency?
Not necessary. You have just model where you have this no resonance. No resonance.
So capacitance is just needed to have the coupling.
Produce interaction, and then question is what is the quantum state? Because in classical state you have just red, green, for example. And but in quantum case you have superposition of states in single element, and then question is how you entangled in a huge system this state.
Many body problem.
Yeah.
Okay,
this
thanks.
Exactly.
Any further questions? Okay, let's thank the speaker again.